So we're supposed to find the volume of the solid generated by revolving the region bounded by y equals 2x, y equals 0, and x equals 1, about the line x equals 2. So we always start off with the bounded region. So first we're going to graph y equals 2x. That's just a straight line with slope 2. That goes through 0, 0. So there's y equals 2x. Then y equals 0 is the x-axis. And x equals 1 is right here. So then here's the bounded region in there. And we're going to rotate that around x equals 2. So here's x equals 2. I put it as a dashed line because it's not part of the bounded region. It's just what we're rotating around. So we're taking this, rotating it around here. So time to put our mental 3D thinking caps on. What does it look like? What's that? A donut, okay. It's not rounded though. So so Abby brings up a good point. It's got a hole in the middle of it like a donut, right? Okay, can we be more specific about a flat tire? All right. Okay, so I've done this a bunch of years. Here's what I think it is. I think it's one of those science fair project volcanoes that has the space in the middle for the thing to erupt out, right? Because it has the slopey sides and the straight middle. Okay, so that's what I got. All right, so we have to find the volume of that. So we rotated this way, right? So do we see circles from the top or do we see circles from the side? You looking from above, you would see circles. So that means that we need to chop off the top in order to get a circular shape. So we're going to chop off the top, then chop off the next layer, chop off the next layer. So we're going to work our way down to the middle. So here's a representative slice. But like Abby said, it has a hole in the middle of it. So that's why these problems today are different. Now our slices have holes in them. Okay, so I've got another visual aid.
I missed the knife again.
So I'm glad you didn't miss both days. No.
Once again, we have no authority, have a knife, try to figure out, I don't know if we can call the hospital.
I know that you're such a stickler for the rules. That he would be the one who'd be worried about that.
Got me there.
Okay, so, but he's right. I don't want to injure myself. Or have cantaloupe fall. So why did I choose a cantaloupe this time? Because it's got a hole, right? Exactly. Get rid of the seeds. So there we go. That's what we got, right? That's what I was trying to draw here. That's what I failed miserably at drawing, right? For those of you at home. That's what I was trying to draw. Good? You picturing this there? Okay, good. Oh, luckily I have my eraser is also a towel. So our job is to find the volume of that cantaloupe slice, right? So how do I find the volume of a slice like that? Yeah, I think I said area, I meant volume. It's the and you went wrong. So volume of the cylinder on the outside minus the volume of the cylinder that's cut out, right? So the formula today is pi r squared h minus pi r squared h. And sometimes I put a big R here. I guess I'll go ahead and do that. Just to emphasize that the radiuses are two different radiuses, right? Two different radii. Okay, so the h. What is the h? That's right. Does everybody see why the h is dy? Okay, so h is dy. And that's multiplied by both of these, right? And it's the same height in both cases, so I could factor it out. Usually we factored things out at the beginning, but I'm going to factor it out at the end. And they both have a pi in them, so I'm going to factor that out at the beginning. So really what I need is my integral with r squared minus r squared. I'll go ahead and find my bounds here. Those are going to be y's. So that's from the bottom of the shaded region to the top of the shaded region. It looks like those intersect at 2, but let's double check that. So if x is 1, plug it in there. Yeah, I'm being way over technical here, right? Clearly it's 2. So that's the point 1 comma 2. So the bounds are 0 to 2. Everybody okay with the bounds 0 to 2? So now we've got to find the two radiuses. So the larger radius is what we need to start with. The larger radius goes from the center out to here. So let's make up a point for this. Let's say it's 1/4, 3/4. I don't know if that's accurate. I don't care if that's accurate. I'm just making up a point for that. Over 1/4, up 3/4. All right, so then in that event, what is this radius here? Yes. 2 minus the quarter. This whole distance here is 2. This distance is 1/4. So that distance is 2 minus that quarter. This is huge right here. Is everybody 100% okay with 2 minus 1/4? Okay, so in general, though, that's the 2 minus the x value of the point. On the point that's on the slanty line, right? So I'll call that x2, I guess. Because it's a little bit awkward because there's 2 different radii, so I'm going to have 2 different x's in my formula. So the big radius is 2 minus the x on the line. Okay, now for the smaller radius. That's the distance from here to here. So what's that? Yeah, go ahead, Nate. It's 1. does it change? It's always 1. Even up here with my other slice. The outer radius changes, that's why I need a formula for it, but my inner radius is 1 no matter what, because this is a straight up and down line, so the inner hole doesn't change. So the inner radius is 1 no matter what. Now it's not this 1, it's that 1, so technically it's 2 minus 1, right? So maybe if you want to follow a method, you'd put a 2 minus 1 in there. So it kind of matches up with the 2 minus x here. Okay, so I thought I was going to have 2 different x's, but so maybe that x2 is a little extra, because this doesn't change. But sometimes you'd have an x over here in this formula, so that's why it's good to have 2 different x's sometimes. All right, so then last thing I have to worry about is that's not good because I got y's in my formula. So I need a formula for x in terms of y. So I need to solve this for x. Well, clearly that's 1/2 y equals x. So that's going to be pi times the integral from 0 to 2 of 2 minus 1/2 y squared minus 1 dy. In the same step, I squared 1, which is 1. Okay, now I need to FOIL this out. So that's pi times the integral from 0 to 2 of 4 minus 2y plus 1/4 y squared. Then I can combine the 4 and the 1 and make 3, so I got pi integral from 0 to 2 of 3 minus 2y plus 1/4 y squared. Then take the antiderivative. Then plug in the 2, plug in the 0, subtract. So we got pi times 6 minus 4 plus 8/12, which is 2/3. 2 2/3 pi, so that's 8 pi over 3. Good. All right, for part B, I'm going to change what I rotate around. For that, I'm going to rotate around y equals -1. So same shaded region. So there's my shaded region. Still, now y equals -1 is down there. So now I'm going to rotate this way. So circles can be seen from the side instead of from the top. So that means we need to chop from the left to the right now. So when we get to the middle, our middle slice will look like this. So the cantaloupe slice is now sideways. Instead of up and down. I guess I'll make it look 3D. Or I guess I'll attempt to make it look 3D. Okay, so the new topic for today is our slices have holes in them. They're cantaloupe slices instead of watermelon slices. So the difference is that when you find the volume of a cylinder with a hole in it, you have to use this formula, pi r squared h minus pi r squared h, instead of just pi r squared h. So that's the new topic for today. So we're using that formula because our slices have holes in them. But we usually just factor out the pi, and we just usually factor out the height and put it at the middle, or at the end, sorry. So in this case, what's the height? Dx this time, because the height's traveling left to right. That's a critical decision. Does everybody see why our height is dx? All right, so dx is our height. And then in here, we're going to have a radius squared minus another radius squared. This time our bounds are 0 to 1. That's still the point 1, 2, but left to right, it's going from 0 to 1. So I got the less tough stuff out of the way now. Is everybody okay with all of that? So now that sometimes the radii are kind of tricky to find. So the bigger radius goes from here to here. So let's pretend that that point is a half comma 3/4. I don't know why I switched from 1/4 3/4, but whatever. Let's pretend that's a half 3/4. In that event, how far is it from there to there? Close. It's not 1 1/2. It's 1 3/4, right? Because the 3/4 is the distance there. And so now it's 1 plus that 3/4. So some people would write down 1 plus 3/4, which is 1 plus the y value, right? Some people like better this. I'm fine with this. I like this better. Some people like this because it's more consistent. Because in the last problem, we were taking 2 minus x, right? So this time, we're taking the same thing and subtracting. Okay, so I usually just go with the 1 plus y. Is everybody okay with that? Okay, then this is a consistent 1 again. So the other radius is 1. I'll show you the next example. We'll have 2 different radiuses that are changing. So there'll be a formula here and a formula here. Okay, not allowed to mix x's with y's. So then I have to replace this y with what it equals, but the y equals 2 times the x. So that's the pi times the integral from 0 to 1 of 1 plus 2x minus 1 dx. 2x is squared, of course. And then from there, it's just the same algebra as we've been doing. Got to FOIL this out, and then take the antiderivative, plug in 1, plug in 0, subtract. So I'll just write down what the answer is for that one. Don't need to go through that. Comes out to 10 pi over 3. All right, so for example 2, got find the volume of the solid obtained by rotating or revolving the region bounded by y equals cosine x, y equals sine x, and x equals 0. And we're going to, by revolving that about the line, or about the x-axis. So as always, we've got to get the bounded region first. So we have to graph y equals cosine x. Does cosine start up here or down here? Cosine starts up, right? Because the cosine of 0 is 1. So that's the graph that is up here and then comes down. And then sine of x starts at 0, 0. So it goes through there. And then x equals 0 is the y-axis. So there's the bounded region. Now, technically, there'd be a bounded region here also. So I'm going to specify here that we're in between 0 and pi over 2. So that means we're definitely talking about this bounded region. So I don't need to worry about this. Okay, so we're taking that and we're rotating it around the x-axis, so it ends up going this way. So it looks like maybe, I don't know, an ashtray, that little divot on the inside. Or if you had a canoe and you'd rotated a canoe around, you'd get the same kind of a solid, right? See the front of the canoe? Does everybody have at least somewhat a picture of what this thing looks like? Okay, so then circles are this way. So we need to slice off from left to right to get circular objects. Is everybody, that's tough for people to visualize sometimes. Usually there's one or two people in the room that aren't sure about what I'm saying right now. Is anybody willing to admit that you're one of those? Okay, thank you, no. So since we're rotating like this, if we cut the top off, we wouldn't get a circular thing. So we've got our canoe here, but it's on its side. If we just cut the top of the canoe off, we get this weird little swivel thing that's not circular. But if we cut off the very left side, because a rotation was happening here, we would get a circular thing off of the left side. That's why we're going to cut that first. And then cut, 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 keep cutting and getting a bunch of those. Are you better now? A little, but not 100%. Yeah. I wish I knew what to say right now to get it to 100%. I don't know. But we're better. So if we keep talking, we'll get to 100%. So there's my inner slice. Yes.
Is that like smaller circle with the radius? Is that always going to be that
Yeah. Yeah, because the lines create the 3D figure. And so when you create that 3D figure, the lines will affect what the radius is. Yes. All right, so it has a hole in it again, so it's pi r squared h minus pi r squared h, so it's going to be pi r squared minus r squared dx this time, right? So then the bigger radius goes from here to there. So it's the y value on cosine. So I'll put y of cosine there. And then the smaller radius goes from there to there. So that's still an up and down distance, so it's a y value on sine. Now, in the last two examples, we had to subtract or add, right? Why aren't we subtracting or adding this time? Well, there could be two different variables where we'd have to subtract or add, though. So that's not why. Yeah. It's because the x-axis is what we're going to, right? So I guess in a sense we're subtracting 0. But the y value is just the distance. When you plot a point, you go over, and then you start at the axis and go up. So the y value is already the radius. Whereas over here, the radius was this y value plus an extra bit to get to the rotation place, right? So it has to do with the fact that we're not rotating around the axis. That makes the radius bigger or smaller than just the y value or the x value. Okay, so this is the y on cosine and this is the y on sine. Everybody okay with that? So the y value on cosine is obviously cosine of x, right? So that would be cosine squared minus sine squared. The y value on sine is sine of x. I didn't do my bounds, so I need to do that as well. From left to right, it starts at 0 and ends at whatever this point is. So cosine and sine hit each other at where? Cosine of pi over 2 is 0. Sine of pi over 2 is 1. So no. Yes. They hit at pi over 4 because they're both root 2 over 2, right? On the unit circle, pi over 4. So you were guessing pi over 2 because of this, right? But that was just there to eliminate that other bounded region so that I wouldn't include that. There have been problems where this clue was the bounds, so that's why I kind of jumped to that conclusion. But the only reason this was here was so that we didn't have this second bounded region. We just had this one bounded region. But this is the point pi over 4 comma root 2 over 2 right there. So this is going to go from 0 to pi over 4. Basically, we just solved in our head just then when the sine of x equaled the cosine of x to find out the intersection between them. And that happens at a 45-degree angle, aka pi over 4 radian angle. Okay. Okay, then this antiderivative is tough. Cosine squared minus sine squared. I don't know how to take the antiderivative of cosine squared. I don't know how to take the antiderivative of sine squared. So luckily there's an identity for cosine squared minus sine squared. It's cosine 2x. So I've got pi times the integral from 0 to pi over 4 times the integral of cosine of 2x dx. So from the step down there to the step up here, I just used the identity that cosine squared minus sine squared is cosine 2x. Okay, then the antiderivative of cosine is sine. So this is a good start on my antiderivative, because the derivative of sine of 2x would be the cosine of 2x. But when you take the derivative of sine of 2x, you get an extra 2 that's popping out, right? So we need to compensate that by multiplying by half. We're doing backwards chain rule here. So then that's from 0 to pi over 4. And it's going to end up being multiplied by pi. So then we have 1/2 times the sine of 2 times pi over 4 minus 1/2 times the sine of 2 times 0. All that's going to be multiplied by pi. Two times pi over 4 is pi over 2. Sine of pi over 2 is 1. So that's 1/2 times 1, which is a half. 2 times 0 is 0. Sine of 0 is 0. Half times 0 is 0. So the final answer is pi over 2. Yes, Jarvis.
How do you know that the area isn't like the area between 0 and pi over 2 that's like actually connected to the x-axis?
Yeah, you were saying just because x equals pi over 2 wasn't part of your bounding, So there wouldn't be anything bounded there by,
Like the part that's actually connected to the x-axis.
oh, this?
Yeah.
The y-axis was never mentioned. Or sorry, the x-axis was never mentioned in the bounding. So remember, we have to ignore that unless it's mentioned. Now, the y-axis was mentioned. Well, they mentioned it as x equals 0. But, so that's why that is part of the bounding. But, so remember early on I said you're going to want to include the axes in your bounded region because they're there, right? Because obviously you're going to draw in the axes when you graph something. So we were supposed to ignore this because it wasn't mentioned as part of the bounded region. Good. That's a great question. But this was included because they said x equals 0. Or they could have said the y-axis too. Any other questions? Yes, Abby.
Because they said that was also bounded by y, or x equals 0, is that why we didn't include the right half of the graph?
Yes.
Okay.
So for two reasons. Because this,
Right, but like, wouldn't pi root 2 be this way, so there's like,
yeah, I don't know exactly what you're saying. Say it again.
there's another, the other, you know how we looked at the other half of the graph?
Yeah.
No, the right half.
Ah, over here.
Yeah, and we don't include that because it said it was bounded by the x.
I think the best way to explain that is yes, they want the thing bounded by all three curves.
Okay,
And so this is bounded by all three. This is just bounded by two of them.
gotcha.
That'd be one reason. Then the other reason is that other bounded region goes past this. So that would give you a second clue that it wasn't that other bounded region.
Okay.
Good. Any other questions?